Okay, welcome back to Calculus 1. This will be lecture 6 of the course. And in this lecture, we're going to start talking about derivatives. So previously, we've delved deeply into the concept of the limit, which is the first concept that you need for calculus. And now we're moving into the second big concept, which is derivatives and differentiation. Okay, so this will be section 2.1, and we'll call it Introduction to Derivatives. Okay, derivatives. Okay, now, so the best place to start with derivatives is with the tangent line problem. So let's start by describing what this problem is and see how this motivates the idea of differentiation. So let's start with a circle, and let's see, maybe that's the center. 1, 2, 3, 1, 2, got here. Now we'll see if I can draw a circle here. There we go. Not the worst circle. Okay, so here's your radius. Okay, now in the case of a circle, a tangent line is an easy concept. So we would say that there's a tangent line here, okay, at the point P on the edge of the circle. Now, for the circle, right, it's an easy case, right? In the case of the circle, the line that is tangent to the circle at a given point, in this case P, is going to be the line that is perpendicular to the radial line at that point. So basically, you got a right angle with the radius of the circle and this line P. And so that's the idea. That's the sort of natural starting point for the idea of the tangent line. Okay, now the problem is somewhat more conceptually challenging in the case of general curves. So well, let me just to be clear here, the tangent line of a circle is the line that touches the circle at point P. All right, and we might technically say that only at point P. And is perpendicular to the radius, the radial line. Okay, so that's kind of what we've said. Now what happens in the case of more general curves, right? So let's just kind of sketch in some examples, and we'll see. It's not quite as clean. Let's say I got a curve that kind of goes like this, okay, and the tangent line here would look something like this, right? If that's P. Another example. What about, a curve that kind of goes like this? Well, if we've got a point P here, then we might say that the tangent line is the line that kind of cuts like that. And then another example. What if I've got a point or curve like this, and I'm interested in the tangent here? Well, then it's gonna kind of go like that. Right, now, a common way of thinking about tangent lines, so it's sort of a common way of thinking about it intuitively, is to think of the tangent line as the line that touches the curve at exactly one point. right? So that's kind of intuitive in some examples. For example, here, right, you could imagine, you know, this line here just touching a single point here, right? You can imagine that. Now, in this case, it's poorly drawn, but you might be able to imagine that the tangent line is the line that kind of cuts through this curve and cuts through in such a way that it touches a single point. And similarly here, like this example here is similar to the first. Of course, like technically speaking, it does cross the line elsewhere, but we're really only interested in being able to say that the tangent line touches the curve in the neighborhood of the point of interest. Okay, so this is a loose way of thinking. We'll get into like some more specific and more rigorous criteria in a minute, but this is kind of a loose way of thinking about it in an intuitive way. The problem of the tangent line essentially boils down to finding the slope of the line that is tangent to a given point P, right? So we're actually kind of more interested in the slope here. And let me just kind of draw a diagram here, and we'll get into this. So let's say I've got a function here. Okay, now on this curve, we're going to denote 2 points here. This is going to be C comma FC, right? That's the ordered pair, right? So this is obviously C, and then FC would be over here. And a second point right over here, this is going to be C plus some distance. Okay, so whatever delta x happens to be. And that we're going to have an ordered pair there as well. And so this is going to be C plus delta x, that's the x coordinate there. And then, of course, the vertical distance would be f of C plus delta x. Okay, like so. Okay, so just for clarification, right, these points are evaluated at C and C plus delta x. Now, let's think about the triangle that's created here. Okay, so this distance here is delta x, right? Right, because here you're C, this is C plus delta x, so if you were to subtract C plus delta x minus C, you get delta x naturally. And so then this is going to be whatever f of C plus delta x is minus f of C, right? And this is going to be the delta, your delta y, your change in y. Okay, so now keep in mind then, you may recollect from pre-calculus that the slope of a line, right, now what we're really talking about is the line that cuts through these 2 points, straight line. Okay, the slope of this line is going to be equal to y2 minus y1 over x2 minus x1, and so that's going to be the change in y divided by the change in x. Okay, so that's the sort of the framework from which the derivative is going to be derived. Now, let me scooch this up a tish. Now, so we're going to let dx denote the change in x, and dy denote the change in y. Okay, we're going to let the ratio of these two is going to be the slope of the just an arbitrary secant line, right? So we could write, as I have here, m is equal to delta y over delta x, which is going to be equal to, what's delta y? Well, it's going to be f of C plus delta x minus f of C divided by delta x. Okay. Well, so technically this would be C plus delta x minus C, but we just kind of skipped that step, right? Now, this guy right here, you may recall from pre-calculus, you probably saw this, possibly even in algebra, maybe like algebra 2 or something. This is what's called the difference quotient. Okay, so the denominator specifically is the change in x, and the numerator is the change in y. Okay, So what we want to be able, so keeping this picture in our mind, the idea with the derivative can be sort of summed up like this. All right, let me try to draw a reasonable picture. Try is the key word there. So let's say I've got a curve, okay, and I've got some point down here, which I'm just going to call P. Okay, now and then some point a little further up the curve, and I'm going to call that guy, I'm going to call that point, well, that's just the starting point, right? And so between these two, there's going to be some straight line, right? Now, if I were to bring this closer, let's say we bring it down to here, right? There's going to be a new secant line defined there that cutting through those 2 points, right? So this could be like secant 1, and this could be like secant 2. And so we could do it again, right? We could kind of go like this and get a secant 3, right? And the idea here is that these points are getting closer and closer, right? Till eventually I could define a secant point, or a second point that's very, very close to P. Right? I could define a secant line that's very, very close to P. Right? So if you imagine these 2 points getting progressively closer to one another until eventually they are arbitrarily close. Okay? Secant 1, secant 2, secant 3, secant 4, secant 5, right? Until you eventually would arrive at the line that is virtually identical with what we would consider the tangent line at P. Right? That's the idea behind the derivative. All right, so if I want to be able to find the tangent line at P, this would be one way to do it, right? I could start with a point that's a little ways away, figure out what the slope is. I could move the point closer, find the new slope, move the point closer, find the new slope, move the point closer, and so on until I'm dealing with a point that's so close to P that it's indistinguishable from P. Okay. Now, what you may be thinking as you see this, what may be coming to mind is the idea of a limit process. So this may bring to mind a limit process, right? So we've seen limits, right? The idea of getting arbitrarily close to a point, what's the value of the function, that kind of thing. But this idea of a derivative, the idea of is going to kind of take the concept of a limit and apply it to this kind of a process. Okay, so let's go ahead and define what we mean by this tangent. Let's kind of make this a little more formal. So if f is defined on an open interval C, okay, and, well, so here's the big and if the limit, now here's the limit, so this is going to be the limit as delta x goes to 0 of delta y over delta x, which we could rewrite in more more like explicitly as the limit as delta x goes to 0 of f of c plus delta x minus f of c, all divided by delta x. And what we would say, as we saw earlier, is this is the slope. So if f is defined on an open interval C, and if this limit exists, okay, then the line passing through the point C comma f of c, okay, with slope m is called the tangent line to f at C. Okay. Okay, so here's the idea. I mean, we talked through the idea, right? Like if I want to know, if I want to be able to figure out what the tangent line at P is, this would be one way to do it. Start with a secant line, make the secant line ever tighter around the point P, and do this until essentially the 2 points that are defining the secant line are arbitrarily close, meaning infinitely close, meaning basically identical. Okay, and more formally, what we would say is that if f is defined on the open interval around C, and if the limit, this limit is delta x goes to 0 of the change in y over the change in x, which is the same thing as the limit as delta x goes to 0 of f evaluated at the latter point, C plus delta x, minus f evaluated at the point of interest here, all divided by the change in x. That's going to equal the slope. If that limit exists, right, then the line passing through the point C of FC with slope m is called the tangent line to f of C. Now, naturally, there's going to be only a single line that does this, right? So if this is your curve, that's your point. Okay, there aren't going to be 2 points. There will not be 2 tangent lines at P, right? Now, hopefully that's kind of obvious why, but you know, specifically there won't be 2 tangent lines at P with different slopes. You know, you might be able to say there's 2 lines, but they have the same slope, essentially the same line. Okay, and so that's why this here kind of defines a unique tangent line. Okay, all right. So let's that's a lot of theory, a lot of calc theory. So let's take a pause and look at an example and see how this might work, how this limit in particular functions. So let's see an example here. So find the slope of the graph of f of x equals 2x minus 3 at the point 2, 1. Right, so this is an obvious one, right? I mean, we don't need to do anything fancy here to see that the slope is 2. This is a linear function, right? So this is already a straight line. But let's start with this simple example just to see how it works, and then we can take more interesting examples. We'll do a more interesting example immediately following this. So kind of following the definition that we just talked about, let's let C equal 2, right? That's the point we're interested in. 2, 1, so the x coordinate there is 2. So let's consider the limit as delta x goes to 0 of f of, now it's C plus delta x, so C is 2, so it'd be 2 plus delta x minus f of 2 divided by delta x. Okay, now here's the part that trips up a lot of folks, you know, and specifically this next step is what is why the difference quotient is introduced in pre-calculus, just to kind of make this a little more straightforward for people. But what we're doing when we say f of C plus delta x, this is the argument of this function, right? So everywhere you see an x, you now have to plug in a C plus delta x. And this should be a 2 here. We know what C is. Okay, so specifically I would have for this first piece, I would have 2 times x, x is 2 plus delta x, minus, right, 3. Okay, so that's this piece. And then minus f of 2, which we got to plug that in there, so it's 2 times 2 minus 3. Okay, so, and then that whole thing is divided by delta x. Now, just make sure this is clear that this part here is f of 2 plus delta x, and this part here is f of 2. So that trips up basically like everybody the first time they see it. So just make sure that that's kind of clear. Okay. Now, what ends up happening, and when you encounter the difference quotient in your pre-calculus course, what you discover is, oh, this thing is kind of special. There's a ton of cancellation, a ton of cleanup that takes place. And so this would be like the limit as delta x goes to 0. Let's just expand these things, and we would get 4 plus 2 delta x, and then minus 3, and then minus 4, and then plus 3, all over delta x. And then, of course, everything here combines, right? So 4 minus 4, 3 minus 3. So those two basically drop out. And I've got the limit as delta x goes to 0 of, what is it? 2 delta x over delta x. And so then the limit as delta x goes to 0 of, now the delta x's cancel out, right? You can think of them as a variable. Okay, so what's the limit of a constant function? Well, it's just the constant, right? So the limit of delta as delta x goes to 0 of 2 is 2. Okay, and so this is the slope, right? Remember, this is this guy right here tells us the slope of the tangent line at the specified point. Okay, so the slope is 2. Well, this is kind of an obvious example, right? Because we already kind of knew that the slope is 2 because this is a linear function and the slope is the coefficient of the x variable. We already kind of knew that. Let's take a more interesting example then, and then I think here's where you'll kind of see the power of the derivative. So here is another example. Let's consider the function f of x equals x squared plus 1. And let's talk about the point x equals 0 to begin with. Okay, so the x coordinate is 0 here, and so obviously the point x comma f of x would be 0 comma, and then if you plug a 0 in here, so it would be 0 comma 1. Okay, so let's remember what this function looks like first. Okay, so here's my xy coordinate. This is a function that is going to cross here like this. Okay, not drawn particularly well, but it's going to cross through this point here, 0, 1 in particular. Okay, so the plus, this is basically the x squared function shifted up 1 unit because of the plus 1 here. So let's plug this guy into our limit here. So the limit as delta x goes to 0 of f of, and in this case it's going to be, well, c plus delta x, and c is 0. I'm just going to leave the c in just because I want to get kind of down to a very kind of a more basic version of it, or more general version, sorry. So c plus delta x, okay, minus f of c all over delta x, right? So let's plug in the actual function here. So instead of f of c plus delta x, what I need to plug in is c plus delta x squared plus 1, right? That's x squared plus 1, and everywhere you have an x, you're going to plug in a c plus delta x, right? So the function looks like that. And then minus x squared plus 1, okay, and the whole thing divided by the change in x, delta x. All right, and then, just like before, we're going to expand this thing. And when we do that, you're going to, so this is c plus delta x quantity squared, so you'll go c squared plus 2c delta x, and I'm going to put that in parentheses just to make sure that people recognize that's together, plus delta x squared. Okay. And then over here, this is going to be, so just basically kind of moving things around here. You'll get, oh, sorry, and then I have the plus 1 here as well. And then over here, I'm going to have minus x squared minus 1. Okay. Oh shoot, I'm so sorry. This is supposed to be a C here. That means this is a C as well. Okay, sorry about that. I kept harping on people to do it right, and then I did it wrong. So f of C evaluated would be C squared plus 1. Okay, and then basically moving the negative sign here, and then this whole thing over delta x. All right, now just like before, a lot of stuff cleans up here, and so the limit as delta x goes to 0. And so what happens here? Well, the c squareds, they go away, right? The 1s, they go away. And so I'm kind of left with this delta, all these delta x terms. So let's write those out. So 2c delta x, okay, plus delta x squared, all divided by delta x. Okay, now there's a lot of algebra we can do yet, so we can factor a delta x out of the top here. And I'm just doing this very explicitly, but you can, if you see it, then you can kind of see what's going on here. But I'm just going to make sure everybody can follow along. Right, so we can factor a delta x out of this term and out of this term, and that's what you do here. So these two will cancel. And what we have is the limit as delta x goes to 0 of just this piece. So 2c plus delta x. All right. So then we can take the limit, right? Take the limit here. What happens as delta x goes to 0? Well, basically this term here just goes to 0, right? And so the whole thing is equal to 2c. Okay. Interesting. So now remember here, we know we have a specific value of c that we're interested in. In particular, we're interested in c equals 0, right? The x term is c, right? So if I plug in, if I think of this as m in general, then I can evaluate m at 0 at c equals 0, and I would get 2 times 0 equals 0. So this is telling me that the slope of the tangent line of x squared plus 1 is 0 at the point 0, 1. Does that make sense given what the function looks like? Yeah, of course it does, right? Like this is the point of interest. This is the lowest point on the curve, and so the tangent line is horizontal there, right? That's the nature of a parabola. That lowest point will have a tangent line of 0. Now, one of the benefits in doing it this way and just kind of plugging in the c is that when you get down here to the end, you have sort of a general form of what the tangent line slopes are for any c, right? So if I were to say, consider the same function, right? For the same function, for f of x equals x squared plus 1, find the slope of the tangent at maybe the point -1, 2. This is another point on the curve, right? So remember our line looked something like this. All right, so here was 0, we found that one. And so if I go over to like -1, maybe it's there. And so now I'm interested in this. So what's the slope there? Well, we know that the slope is equal to 2c. So all you need to do is plug in your c here. So the slope at -1 would be equal to 2 times -1, which is -2 in this case. And so that's telling me that this guy here, this slope here, is -2. Well, what about at +2? Well, the slope at +2 is going to be equal to 2 times 2, which is 4, right? So here we're saying the slope of the tangent line is 4. Nice, right? So basically, if you leave the c variable in the tangent slope formula you can easily find the slopes at any point on the curve. Okay, and that's gonna lead us very directly into what is going to be defined as the derivative. Okay, so the derivative is the next thing that we need here. So this is one of the big ones for calculus. So the derivative, okay, of f at x is given by, and the notation we'll get into in a second, so it's f prime of x equals the limit as delta x goes to 0 of what we just were looking at, x plus delta x evaluated minus f of x over delta x. Okay, provided that the limit exists. Okay, and so what we say then is for all x for which this limit exists, f prime of x is a function of x. Okay, so basically we have a new function here called f prime, which is the derivative of the original function f. Now, one of the key things here to note is that the derivative of a function is also, so the derivative of a function of x is also a function of x. Okay, this new function provides you with the slope of f at any point. Okay, so this is key. Okay, the derivative of a function f of x, right? The derivative of this function is also a function. Okay, and specifically of x, right? Okay, and this new function tells you the slope of f at any x. Okay, so that's kind of the powerful thing here, right? All right, so we did two examples where we basically used this limit to find a specific slope of a specific tangent line at some specific values of x for a specific function, or two actually specific functions. Now what we're saying is that in general you can define a function by applying this limit process to the original function, and that function is called the derivative of f. Okay, now let's talk a little bit more, and then we'll do some examples. Don't worry, I know that we might be getting a little bit away from, like, things may seem a little fuzzy. We'll do some examples and set things a little more, make things a little more transparent in a second. So there's some terminology and some notation that we just need to kind of discuss here. So the process of finding the derivative of a function is called differentiation. Okay, so this is the process of finding the derivative of a function. Okay. A function is called differentiable at x if the derivative of f at x exists. Okay, so differentiable is another term that we'll use. Differentiable, so differentiation, then differentiable. A function is called differentiable at a specific x if the derivative of f at x exists. Okay, so so basically, like if that previous limit that we just looked at, if it exists for a particular function at x, then we say that function is differentiable at x. And then this kind of differentiable idea can extend to intervals. Right, so if all of the x in a particular interval, are differentiable, then we say the interval is differentiable. Okay, so these are just two terms that we need to make sure we understand. So there's the derivative, that's the name of the actual function, f prime. F prime is the derivative. Finding f prime is, to find f prime, we have to differentiate f, right? So f prime is the derivative. To find f prime, we differentiate f, and we say that f is differentiable at x if f prime of x exists. Okay, so I know this can be a little, some of this terminology is a little tricky at the start, but you'll catch on pretty quick, I think. And then there's some notation. Okay, so this is just like the terminology piece of it. There's also a lot of notation here. So f prime is the one we've seen. So the derivative function in particular. So f prime of x is commonly used. Other notations exist as well. So this would be, so like an example would be f prime of x equals 2x. That would be a way to write the derivative of f, right? And another example would be the y prime notation, right? So everybody, you kind of know that, sometimes a function will be denoted using the function notation. Sometimes people will use, y equals 2x instead. And so in that context, you can also use the prime notation on the y variable like this. And so this would be the derivative of y. Okay. Another notation that's a little bit different would be this. This is literally read as the derivative of y with respect to x. Okay, and so what we could say here is that dy dx equals 2x. The derivative of y with respect to x. Right? And yet another way to discuss the derivative would be to do something like this. So this would be the derivative with respect to x of the function f of x, right? And so you might write it like this. Right? You can kind of name the derivative. It sort of depends on your way of thinking, and probably the least used, but you still may see it sometimes, would be like this. Okay, this is the derivative of x, the derivative of y with respect to x, and so you might see it in context of an actual function. Someone might write like this. Right. This one gets used very little, but these are all very common, and I would say even we'll be using all of this notation throughout the course. And I think as you get into it more, as you start to develop more intuition about this, I think you'll start to use these things interchangeably. Okay, next, let's do an example where we explicitly find the derivative using the difference quotient, using the definition. So find dy dx if y equals x cubed plus 2x. Okay, so here we're kind of beginning to try to use a little looser notation. All right, so dy dx, that's just the derivative of y with respect to x. So dy dx is equal to, now this is that limit. The limit is delta x goes to 0 of f of x plus delta x minus f of x over delta x. Okay, so that limit. And we have a specific function here, right? X cubed plus 2x is the one we're interested in, so let's plug all that in. So the limit is delta x goes to 0 of, and so here we have x plus delta x cubed, okay, plus 2 times x plus delta x. Okay, so that's the f of x plus delta x piece. And now minus f of x would be minus x cubed plus 2x. And the whole thing divided by delta x. All right. So far, so good. And now we have to expand everything. And so here's where I might run out of room. Let me just actually use the whole width here. So just expanding, each of these pieces, we would get something like x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. So that's just expanding this part. Okay, so just you have to remind yourself of sort of how to think about this is like a plus b cubed. So if you've seen that formula, you know kind of how this runs. And then this other pieces they're more straightforward. So it'd be plus 2x plus 2 delta x. And then this piece down here, you just distribute that negative minus x cubed minus 2x. And then divide the whole shebang by delta x. Okay, and now here's where a lot of the cancellation is going to come into play. And so after you've done all the cancellation, you should get something that looks like this. So you get 3x squared delta x plus 3x delta x squared, right? So these two stick around. And then the third term is also stays in the function, and then the last delta x term as well. Okay, everything else drops out. So for example, the x cubed here cancels with that x cubed. The plus 2x cancels with the minus 2x. And actually that's only those four. Okay, and then all over delta x. And then we can just, like we did previously, we can factor delta x out of the whole thing. So we factor delta x and we get 3x squared plus 3x delta x plus delta x squared plus 2, right? All over delta x, and the delta x's cancel, and so what we're left with is 3x squared plus 3x delta x plus delta x squared plus 2. Okay, now, I mean, after you do a few examples of this, you kind of get the sense of it, right? Like basically what needs to happen is the delta x needs to come out of the denominator in order for the limit to work. And once it does, many of the delta x terms will go to 0, and the terms that don't retain the delta x after all of the simplification is done are going to be the terms that are left after you take the limit. And so taking the limit, we can see that this whole term goes to 0, as does that one. And what we're left with is 3x squared plus 2. Okay. So what this means then is that if f of x equals x cubed plus 2x, then f prime of x equals 3x squared plus 2. Okay, so here's your original function, and here's the derivative of that function. Okay, now what's the relationship between the derivative and the original? Well, the derivative tells you the slope of the original function of the tangent line at any point in the domain. Okay, so for example, if someone were to say, what's the slope of the tangent line at x equals 0? Well, I could just find f prime of 0. The slope is 2. What is the slope of the tangent line at x equals 1,000? Well, I plug 1,000 into this, and whatever I get, that's the slope of f at the point x equals 1,000. Now, it's very important to kind of remember that when we say what is the slope of the tangent line at a particular point, what we're really asking there is what is the slope of the function, right? Because the tangent line is the line that touches the function at a single point. And so when we ask what's the slope of the tangent line, what we're asking is what's the slope of the function at that point. Okay, so the derivative has tremendous applications in physics. So all of this, if you go into physics, you'll be using derivatives to identify the instantaneous velocity and the instantaneous acceleration and all of those kinds of things, as well as many, many others, but those are sort of the most immediate applications. But so just being able to identify the slope of a function at a particular single point is something entirely new that you cannot do without these calculus tools. So I think I'm going to split this lecture into 2 pieces, and so we'll be back with a lecture B to accompany this one.